Alright, so welcome to tonight's video. We're going to finish up, excuse me, target 16 here. We left off with finding the derivative of a to the u, which we saw was a to the u, natural log of a, and then the derivative of whatever u is, which is a lot like e to the x, except you got the conversion for a different base. So we'll look at the next one. This says, at what point on the graph does the tangent line have a slope of 21? Well, first we're going to want to find, our derivative here so we can find the slope of our tangent line. So our derivative here, our dy dx, will be 2 to the t. Oops, I should change that to dy dt because that's a variable. dy dt will be 2 to the t natural log of 2, because 2 to the t, and then it's not e to the x or e to the t, so we convert to our base. So we're looking for where that derivative, 2 to the t plus ln of 2, is equal to 21. And so we just need to solve for t. We'll divide both sides by natural log of 2. 2 to the t equals 21 over the natural log of 2. And then we have an exponent. We'll convert that to a log to solve. So t equals log base 2 log base 2 of 21 over the natural log of 2. Alright? So that's where t is. If we wanted to approximate it, we could punch it in the calculator and do so. Alright, so here's a calculator-based problem we're going to work through. What I would do is I'd start by putting this into your y1, and then calculate your derivative, put it into y2, or you can do the n derive of y1 comma x into y2. That would probably be the best way. So I got those in already. I got my y of t stored in. And the first question we want to know is, what is the temperature of the refrigerator? Well, the milk comes out of the refrigerator. The milk should have the same temperature of the refrigerator when it comes out. The milk comes out at time t is 0. So we do y of 0. The temperature of the refrigerator is 42 degrees Fahrenheit. And then what is the temperature of the room? Well, as the milk sits out on the counter, it's going to approach the temperature of the room. So what we want to do is we want to have the limit of the temperature approach infinity. The longer that milk is out, the closer it is going to get to the temperature of the room. So we're going to let time approach infinity for our y function. Now if you think about this, if you take 0.98 to multiply by itself over and over, because that's a fraction less than 1 or a decimal less than 1, this is going to approach 0. This is going to approach 0, and you're going to be left with 72. So the temperature of the room is 72 because time increases to infinity, approaches infinity, and that's what the temperature of the milk approaches. Okay, when is the milk warming up fastest? Well, what we need for this is we need to find the derivative, and then we find the maximum of the derivative. Alright, so here I've got the graph of the derivative. This is f2 equals d dx of y of x. So that's my y function. I just changed the variable so I can graph it on an xy axis. And according to this graph, we can see the maximum the derivative is when it first comes out of the refrigerator. So the milk is warming up fastest at t of 0. It doesn't ask for the rate, but we could find the rate. f2 of 0, the milk is warming up fastest at 0.606 degrees Fahrenheit per minute at time equals t equals 0. Determine algebraically when when the temperature of the milk reaches 55 degrees. Well, we're not going to do this algebraically. We're going to graph 55. We're going to graph the function. We're going to see where they cross. Okay, so when it happens is right here. We'll do an analyze graph or second calc intersection for those of you with the 84s. We'll find out where they cross, and they cross when the question is when. Your answer is the x variable. And anytime you get an answer, you're going to want to store that. I'm going to store this into A. Oops, invalid input. Store that in A. So now anytime I hit A, it's going to think I mean 28.1 or whatever that is to 5 or 6 decimal places. If you don't know how to do that on an 84, you need to come see me, because there's a really quick and simple way how to store your intersections on an 84. Now, as you continue, at what rate is the milk warming up when its temperature is 55 degrees? Well, we know the time. It's warming up, its temperature at 28.1 minutes, its temperature is 55 degrees. So what we need to do is we just need to go back and put that time into the derivative. And my derivative was stored in F2. And at 55 degrees, I stored that in the A. And we can see the milk is warming up at a rate of 0.343 degrees Fahrenheit per minute, or per minute squared, because, no, per minute, because it was a Fahrenheit and then per minute. So 0.343 degrees Fahrenheit per minute. That's how much the milk is getting warmer. All right. Moving on. And again, pause these if you want to work through them first. Find the derivative of log of a to the x. This is a little different than natural log, but not a whole lot. In fact, we'll use the change of base formula to make it pretty much a lot like it. The change of base formula, natural log of x over natural log of a, our old base. Now, because natural log of a is a constant, we don't technically need to use a quotient rule. We can just treat this as 1 over natural log of a, which is a constant, times the natural log of x. And then when we do our derivatives, our derivative of y with respect to x, we'll do it as a constant multiple, 1 over natural log of a, and the derivative of natural log of x is 1 over x. So you're going to see it's very similar to the derivative of natural log of x, but just like when you change the base of an exponent, you're going to have to account for the fact that you have a different base by doing 1 over natural log of a to account for its base as a instead of your base as e. And that's why I always say use base e if you can, because your derivative is simpler. You don't have this multiplication by a constant. Alright, and then so there's the formula. And again, it's very similar to the formula of natural log of u, except you just got to have the different base accounted for. Alright, so we'll try this. What is, if y equals log base a of a to the sine x, what is dy dx? Now I'm going to do this two ways because there's a long way and a short way. You're probably going to think of the long way right away, so I'm going to do it the long way first. So you're going to do, for the derivative of a log, you're going to do the derivative of what's inside. And what's inside is a to the sine x. The derivative of that is a to the sine x, natural log of a, times the derivative of sine x is cosine x. And then over what's inside. What's inside is a to the sine x, natural log of a. And if you notice, this all right here cancels, and we're left with cosine x. Is there a way we could have got that quicker? Oh, yes, absolutely. Look at our log rules. What do we do when there's an exponent? Well, we can bring it out. y equals sine of x times log base a of a. Well, what is log base a of a? Anytime your base of your log and what your value would match up, it's 1. So it's like multiplying by 1, which we don't need to write. And what's the derivative of the sine of x? Well, we all know that. That's cosine of x. dy dx equals cosine of x. Alright. So, in conclusion, these are the derivatives you should know. I'm going to star the ones that are more important. Know that one. Know that one. And also know how to, if you have a really complex derivative, know how to do log differentiation, where you take the log of both sides and expand it. So know these derivatives. dy dx when y equals e to the x is, well, that's easy, e to the x. dy dx for the natural log of x is 1 over x. And likewise, for a to the x, it's the same thing. You're going to do a to the x. But because your base is not e, you need to multiply by the natural log of your base. Same thing for log base a of x. Your derivative is 1 over x. But because your base isn't e, you need to have natural log of your base in there. And I always put it on the bottom for log and on the top for the exponent. Because they're opposites, they're going to go in different places. So that's the rest of Target 16. Again, the stuff we did on video there isn't going to appear a whole lot in AP Test. So make sure you've seen it, maybe get familiar with it, but focus on the stuff we did in class. Have a day.